Hi there, this is Simon Horning with ECE 56800 at Purdue University. Today I'm going to be doing a hardware overview, demonstration, and code review of Lab 2. Today is March 1st, 2026. To start off, we have our hardware set up right here. You can see that we have our computer with Thonny IDE. We have our ESP32. This is an Adafruit ESP32 Feather V2 board. You can see we have one green LED, and over here you can see that we have one blue resistor here. This is a 330 ohm resistor. Then we have one 10K potentiometer. The green LED is connected to the ESP32 GPIO4. This is labeled A5. This is labeled A5 here, so you can see the yellow wire connects to the anode of the green LED, and then that the ground connects to the ground on the ESP32. Next, you can see that the 3.3 volt output labeled 3V here in red. You can see that goes to the positive input of our potentiometer right here, and then that the negative side goes to ground as well. The output of the potentiometer here, this white wire, goes to, you can see A2 on the ESP32, and A2 is GPIO34. We will also be interfacing with the switch on board here. No external wiring needed, but this is GPIO38 for anyone curious. So without further ado, let's go ahead and get into a demo of it. So we will go ahead and hit run. So the year is 2026, the month is 3, the day is the 1st, the weekday, today is Sunday, so that's a 6. The hour is 10:21, so that is 22. The minute is 21. The second is 30, and the microsecond will start at 0. You can see first we get an output Sunday, March 1st, 2026, 10:21 with 30 seconds PM. You can see the microsecond value there as well. And you can see as soon as I hit enter on the microsecond, you can see that the LED started blinking. This is blinking at a frequency of 10 hertz with a duty cycle of 50%. And you can see that twisting the potentiometer has no effect on the value of this. And that's all the output we'll see on here, other than you can see 30 seconds have passed and we have output 10:22:00. So I'll show this again when another 30 seconds passes. If I hit the button once, you will see no output here, although my code does have an optional portion where you can trigger it to tell you whether it's in frequency or duty mode. That is not enabled. Here you can see that another 30-second interval just began. Now you can see if I twist this, it's in frequency mode, so the frequency is very high now. And I can drop this all the way down to 1. So let's leave it at somewhere there. And let's go ahead and we'll increase it a little to show the duty cycle. So if I'll press the button again, and now we're in duty mode. So if I increase it all the way, see it's very bright. And if I decrease it, you can see we can actually go all the way down to 0. So we'll do one more example here where we increase the frequency so it looks like a constant light, and then we'll view the intensity change with the duty cycle. So right now the duty cycle is 100%, it's the brightest. You'll see as I decrease it down to 0, it'll get less bright. Very quickly, we'll just run through the code here. So you can see that we have our potentiometer and real-time clocks and everything all set up here. We have some functions that are in place to do the time and date keeping. We have our analog to digital conversion callback function. We have our switch press callback function and the debouncing. This is that optional section that I mentioned where you can see which mode we're in. This is what takes our user input. You can see we initialize a real-time clock. We print it immediately just to confirm to the user that they have inputted things correctly. This is optional and can be removed, but added in as a nice feature in addition to the lab. Then we have the timer get initialized here for that real-time clock, date time output. Then we have our analog to digital timer, or LED. And then lastly, the switch interrupt request handler, which detects when the switch is pressed. Finally, we run this forever in accordance with the lab instructions, and we get the output that we see below. Thank you.